All right, ladies and gentlemen, welcome to our next episode of Physics with Mr. Barry. Hope you guys are all doing really well out there in coronavirus land. Hope you and your families are safe. But here we go again with some more physics stuff for you guys. Now, today is the first real physics lesson we've had. Everything we've done up to this point has been, as I said, just kind of mathematical things we need to be able to do to solve physics problems. All right, but today we're actually getting into our first theoretical concepts of physics, and most of our physics unit in Science 10 deals with motion. All right, and basically how do we understand how things move, which I know isn't the most exciting thing in the world, but we have to be able to understand how things move, how they actually go from point A to point B. It's how we can actually figure out many things about our universe, especially when you think down to like a particle level. Like we need to be able to understand, in order to understand chemistry, we need to be able to understand how particles move and vibrate in place. To understand why things heat up the way they do, we know that heat comes from kinetic energy. So our ability to understand movement is really important. But it turns out that motion is actually not that easy to study. It turns out that the ancient Greeks used to sit there and go, well, there's no way we will ever be able to figure out how motion works. And they had this whole scenario that I'll explain on Tuesday on why we would never understand motion. But it turns out we do know. So I'm going to come in here with our first lesson today, which is all about uniform motion. And if you guys think about the word uniform just means same. So when I'm talking about uniform motion, really what I'm talking about is something moving in a consistent way. Okay, versus accelerated motion where things change, and we'll get to that one in a few weeks. But before we start, I want to talk about what it means for something to move, which is a really stupid question, right? Like, how do we know something is moving? Whenever I ask this question in class, students always go, well, because it's moving. And I'm like, yeah, of course, we know when something is moving, when we don't. But it's actually not that simple. So I want you to imagine the following scenario. Imagine that you are in the car, and you're just driving down the road, and you're just kind of, you're in the passenger seat, you're hanging out, you're just watching the trees go by, and to you know that you're moving, you know that intuitively, but from your frame of reference, it actually looks like it's the trees that are moving. And it turns out there's no scientific experiment that we can do that would prove to you, the person in the car, that you're the one moving and that the trees aren't. Because it all comes, it turns out it all comes down to frame of reference. All right. So basically, the way I always like to think of frame of reference is, when you're at the train station and you're like walking along the platform as the train arrives. So like you're walking in one direction and the train's coming from the other. And like because the train is moving really quickly beside you, it makes you feel like you're moving faster. Or the opposite, if the train's moving in the same direction you are, it feels like you're moving really slowly because you got this fast train moving past you. It's because your frame of reference has you at a certain spot. Okay? So in science, the way we define how something is moving is actually quite simple. Okay? So imagine I have these two circles and I can move them around like this. All right? The way that we know that something is moving is when I have, we basically pretend we have a straight line connecting them. Okay? So imagine I have this little yellow line that connects these two circles together. Okay? The way we can tell that this red circle is moving compared to the green one is that as I move the red circle, the imaginary line that we drew between the two of them gets longer or shorter, okay? Basically, if there's an imaginary line connecting two things together, that line will get bigger or smaller if one of those two objects is moving. The other way that we can tell if something is moving or not is to, imagine I still have this yellow line connecting the two of them together. The line doesn't necessarily have to grow bigger or smaller, but it could also change directions. So imagine if my little red circle stayed about the same distance, then I have to basically redraw that line here. So that line has now moved. So the line has either changed direction or it changes in length. So the definition of motion in science is that if you connect two objects together with an imaginary line, if that line changes in length, gets longer or shorter, or if that line changes direction, then one of those two objects is moving. All right? And it's hard to tell which one's which, so it's all about which frame of reference. Okay? It's a little bit weird. It's very theoretical. But let's get into a little bit more on the practicalities of this. That's just the theoretical piece. Okay, so, and I'll be honest, I haven't done a great job of drawing these things, so bear with me here. But imagine that what I have here on these little rectangles are tracks showing three different cars, or, yeah, let's go with cars. Three different cars that are moving, okay? And each of these cars has a oil leak. And so imagine that if we look at this top line here, this is where the car started, the circle one. And every time it moves for 1 second, an oil drip falls. So every 1 second, oil falls off the car and drips on the ground and leaves a little dot. Okay, so every second, this car is leaving a little drop of oil as it moves from here to here. Same thing with this one, same thing with this one. The question we want to ask ourselves is, based on the fact that each of these oil drops is 1 second apart, we need to be able to figure out which of these 3 cars is moving fastest. Okay? So I want you to take a second and just think about it, looking at my green, blue, and yellow cars here, based on the fact that every 1 second, these oil droplets are a certain distance apart, which of these 3 cars do you think is moving faster? Just take a quick second to kind of think about that on your own there, and I'll give you the answer right about now. So it turns out this yellow one here is moving the fastest. All right. A lot of people will say it's this one because it kind of looks like it's going beep 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 like that, and so people think it's really moving really quickly, but it's not. It's actually the slowest of our 3. The way that we know that this one is the fastest is because each of these oil droplets is 1 second apart. And what I can see here is between each of these seconds, between this one and this car has moved the furthest distance compared to this one and this one. So it turns out the way we can tell how fast something is going is how much distance it covers in the same amount of time. So every 1 second, this car is going this far, whereas this car is only going this far. So this car took a whole second to go from here to here, which is not a very big distance compared to this to this. This car here is going about medium. Now, I did a bad job of drawing this because the dots are not evenly spaced. I really tried. I even had a ruler on here, but whatever. It's the best I could do. So if these dots are all equally spaced apart, and they should be, then we can assume that our car is traveling in what we call uniform motion, meaning it's saying the same speed every second. It's moving the same distance every second. So the big thing I want you guys to understand when we look at these 3 kind of dotted, leaky car stuff is that there is a huge relationship between speed that I'm traveling, how far I'm traveling, my distance, and how long it takes me to get there. And the idea being that if I cover a bigger distance in the same amount of time, then I'm moving faster. And that makes sense to us. We don't think of it that way, but it does make sense to us. Think about it this way. If you're going 70 kilometers per hour, that means every 1 hour you move 70 kilometers. You cover a large distance. If you're only going 50 kilometers an hour, which we know intuitively is slower, that means that in that same hour of time, you only went 50 kilometers. You went 20 kilometers less, so you're going slower. So these 3 things come together, distance, speed, and time, to allow us to figure out how quickly something is moving. All right? And when you think about the units for speed, like that we do when we're driving, like kilometers per hour, notice that I have the unit for distance and a unit for time. Kilometers, distance, hours, time. So we can actually link distance and time together to figure out how fast something is going. All right, so as I said earlier, our big lesson today is on uniform motion, all right? And uniform motion, as I was kind of talking about on the last slide, is when an object travels at a constant speed and in a constant direction. So this thing is not speeding up or slowing down. It's staying at whatever speed it's staying at, and it isn't turning at all. It's always heading east or north or whatever it happens to be, all right? Uniform motion is a kind of weird concept because, and if you looked at the notes, and you should have by now, if you looked at the notes, it's really impossible for something to stay at a consistent speed. If you think about it this way, if I'm traveling from my house to school, as an example, when I first get on the road, the speed limit is like 50 kilometers an hour. When I get onto Deerfoot, the speed limit goes up to 100 kilometers an hour. And let's be honest, some days I'm moving a little bit faster, some days I'm moving a little bit slower, but the speed is changing from my route between school and my house. And so instead of treating things as if, or saying that things always move in uniform motion, which we know can't be maintained over long periods, we study things by looking at what we call their average speed. And average speed is exactly what it sounds like. It's like if you traveled from here to here, from school to home, in this amount of time, this would be the average speed you were traveling that entire time. So yes, some points you might have been going 50 kilometers per hour, sometimes you might have been going 100 kilometers per hour, but your average speed will be somewhere in between depending on how long you spent at 50 versus 100 kilometers per hour. Okay, and we have our formula, and this is our first formula that you guys are going to learn for physics. But the nice thing about how we do formulas in physics is you do not need to memorize them. Okay, all of the formulas that you'll need for physics are on page 6 of your data booklet. And this is the very first one at the top of the page here, which says V equals D over T. So let's talk about what all these units are. D here, and you see this, you see the little triangle? The triangle means it's delta, which means change. Okay, so when I look at my units here, or what I'm looking at here, this D is change in distance. Oh, my cat's here. Okay, the T down here with the delta beside it is going to be change in time. And my V here, and it seems weird to use V for this, is going to be my speed. Okay, so what we're saying is that your average speed is equal to how far you traveled from where you started to where you are now, and how long it took for that to happen. Okay, the delta doesn't come up a lot, but we'll get to some problems later on where it does. For now, just think of it as how far you went divided by how long it took you to get there. And the reason we use a V for speed is that later we'll talk about velocity, and speed and velocity are linked. We use them very similarly in day-to-day talk, but they are different things. We'll talk about that next week when we talk about vectors, but for now, V stands for speed, okay? So this is our first formula. It's a nice, easy formula. There's only 3 variables in it. So we're gonna start looking at problems we can solve. We're gonna go through the 3 example questions on page 2 of your new booklet, the booklet number 2. So hopefully you have that printed off or that you can look at it while you solve problems on another piece of paper. But let's go through those examples on the next page. Okay. So this is our first problem. Again, it's on page 2 of your booklet. It says a car travels 321 kilometers in 2.1 hours. How fast is it traveling? Now, when we solve problems in physics, I like to do it with what we call the GRASP method. Okay, and if you look at the PowerPoint, it's all written there. It's also in your notes. When I say GRASP method, what I'm saying is when you solve a problem in physics, it's always good to first of all write down your givens. That's the G. In other words, list all the things that you know, your known numbers that come from the equation or the question that we're asking. Okay, so we're going to write down what we know. So the things that were given in the question, we are given that the distance is 321 kilometers. Okay, we know that the time is 2.1 hours. Now, if you're not sure how we knew that this was distance and this was hours or time, we just looked at the units. Kilometers has to be distance. That's what it measures. Hours has to be time. Okay, and then it says how fast is it going? So the next step of the GRASP method is to write down what we require. What are we looking for? What are the things we don't know? So here the thing that we don't know is our speed. That's what we're trying to solve for. Now, it seems like a pain to write that down every single time that you're solving a question. I have done this since I was in Science 10 when I was taught this, and I'm telling you it helps you organize things, especially as we go further and further in the physics unit, where you have to figure out what the question is asking you. In other words, you need to figure out what formula to use, and if you write down what you know and what you don't know, you can figure out, okay, what is the formula that links these 3 units together? Right now, we know that our formula, the only one that we have, is V equals, I'm just going to write D over T. I'm just going to ignore the triangles because I'm going to run out of space. Okay, so speed is equal to distance divided by time. Well, we know our distance is 321 kilometers. Okay, we know our time is 2.1 hours. So we call this the analysis step. That's the A in GRASP, is to just write down what formula we're going to use, and if we have to rearrange the formula, then this is the time that we do that. This one we don't have to rearrange because it's already trying to find our speed. That's what we're trying to figure out, so it's already rearranged properly. If you don't know what I mean by what we need to find, it'll make more sense on the next 2 questions, okay? But this one is a nice simple one. So now all we're going to do is plug our numbers into it. This is the solution stage, okay? So this is the S in GRASP. We're going to take what we know and put them into this formula. So our distance is 321 kilometers. Our time is 2.1 hours. I like to use brackets around them. You don't have to. It's just something that I kind of instinctually do. I don't know why. So don't worry about having the brackets there, but I like to have them. And when I divide those 2 in my calculator, 321 divided by 2.1 is 152.1 1.87, or 857, sorry. Let me just quickly undo that. There we go. 857, and then a whole bunch of numbers after it. All right. Whenever we solve a question in physics, we always want to make sure we have the right number of significant digits. So when I go back to my original numbers here, time here only has 2 digits. This one has 3. So my answer needs to have 2 to match this. So that's just our significant digit rules from last week. So when I round this, I'm going to have to get rid of a whole number here. Like I'm going to have to get rid of this 2. And because I'm getting rid of a whole number, I have to use scientific notation. So when I round this, I'm going to go 1.5 times 10 to the power of 2. And then the other thing that we can't forget in physics ever is we have to have a unit. All right. We're trying to find speed. Speed is always measured in kilometers per hour or meters per second. In this case, we divided kilometers by hours. So I know that my unit here is going to be kilometers per hour. Okay. Had I divided meters by second, like if this was in meters and this was in seconds, then my answer would have been in meters per second. Okay. We always have to make sure that it's in one of those two. I never want to see you guys put down like how many kilometers per second you went or how many meters per hour. Those numbers are either too big or too small to have any kind of significance. So your answer for speed should always be in kilometers per hour or meters per second unless the problem tells you otherwise, which won't happen very often. Okay. So that's our final answer for the first one. Nice and simple. Okay. So this second problem, things get a little bit trickier because when you look at what I'm given in the problem, when you look at the fact that I'm given meters per second and the number of seconds, what this means is we're not trying to solve for speed this time because the question is giving it to me, right? And we can tell it's giving us speed because it's in meters per second. That's our unit. So again, if you're not sure what it's giving you in the question, just look what the units are. Meters per second or kilometers per hour will be speed. Seconds or hours will be time. Meters or kilometers will be distance, okay? So that's why the grasp method is really important. It's why it's helpful to write down what you know and what you still need to find. So here, based on the question, we know that our speed is 15 meters per second. And we know that our time is 250 seconds. And then the question says, how far does it travel? Whenever you see something like how far does it travel or what was the distance covered, it's asking for distance, okay? So our unknown here, what we're trying to solve is our distance, okay? Now, remember the formula we get, and the only one that's in your book, is V is equal to D over T, okay? But here, I'm not trying to solve velocity, I'm trying to solve for distance. This is what I want. So what I want to do in physics, what a skill you need to kind of develop is to be able to rearrange formulas to find the unit that you actually want, okay? And this is where I find that students have a bit of trouble, especially if you're somebody who maybe struggles with algebra, okay? So what we want to do is we want to rearrange this formula to get d, distance, by itself. Kind of like how right now v is by itself. When we're done, we want a formula that says d equals something, okay? So we're going to figure out what that something is. And the way we do that is by looking at, or basically undoing everything that we're currently doing to distance, okay? So what that means is we have to look at what's happening to distance. And in this setup, right now we're dividing distance by time, okay? I want to undo that. I want to get rid of this divided by time. So what we have to do is the opposite, because as soon as I do the opposite of dividing by time, the time is going to cancel out, which is exactly what we see when we do unit analysis, okay? So what I'm going to do here is I'm going to do the opposite of dividing by time, and you should hopefully know that the opposite of dividing is to multiply. So I'm going to multiply this side of the equation by time. And what you'll notice is because I'm dividing by time here and multiplying by time here, these two things are going to cancel each other out, okay? Which is good. That's what I want. I want d by itself. The problem is I can't just multiply this side of the equation by time and then not do anything to this side. Because right now, this equal sign means that this and this are exactly the same. So what I have to do is I also have to multiply this side by time to make sure I have accounted for the fact that I did that here, okay? So I'm going to go t times v, okay? But here, nothing cancels out, all right? So what I get when I get rid of everything I canceled is, I'm just going to rewrite this here, is t times v is equal to d, okay? And I did that because I had to multiply both sides of my equal sign by time, otherwise it's no longer equal. Now I actually have the setup I want, right? I have d by itself, and then I have what it equals. But I don't like the fact that it's flipped around here. Normally we like the variable we're trying to find to be on the left. So I'm just going to quickly rewrite that as, oops, my other t went away. I'll draw that back. Okay, so I'm just going to rewrite this as d is equal to v times t. All right. Now I have the setup I want. I have distance by itself. I know my speed. I know my time. All I have to do is take these numbers here and plug them into the equation. So we're going to say our distance is equal to 15 meters per second times our time of 250 seconds. Okay. When I multiply those two things together in my calculator, I get 3,750 meters. Okay. Again, as always, I want to make sure my answer has the right number of significant digits. When I go back to my original numbers from the question, this one has 2 significant digits, this one has 3, so my answer should have 2. So I'm going to round this to 3.8 times 10 to the power of 3 meters. And the reason I did that, the reason I use scientific notation, I should say, is because I have to round it here, which means I have to get rid of whole numbers. So I had to use scientific notation. Okay. So there's my answer for that one. We're going to do one more. Example number 3. This one's going to be the hardest one. All right. So this is the hardest one. And the reason I say that is it's asking us to do a lot. This is a mean question. When I look at it, I go, why did I even put this in here? I also have a spelling error, but it's too late to fix it. So this one says a woman runs 6.4 kilometers per hour. How long will it take her to run 1,200 meters? Express your answers in minutes. This is a mean thing to ask, but it's something we're able to do. Basically just practicing our unit conversion. Okay, so let's, as usual, write down what we know and what we need to find. We know that our speed is 6.4 kilometers per hour. We know that our distance is 1,200 meters. And we just know that from what units they were. Okay, it didn't say the speed was this, the distance was this, but I just know from the units. Okay, what we don't know is time. Right? And I will say time is the hardest one to rearrange the formula for. But before we can even do that, we have a bit of a problem. What I want you guys to notice is that speed is in kilometers per hour. Big highlight there is the fact that it's in kilometers. Okay, and our distance is in meters. So these two things are not compatible with each other. We can't just throw them into the formula and multiply them or divide them or whatever it is that we have to do in this, because we need them to be exactly the same. If this is in kilometers and this is in meters, then I either need to convert this to kilometers or this to meters per second. I know, for my own sake, and I hope you guys feel the same way, that converting meters to kilometers is way easier than converting kilometers per hour to meters per second. So before we can even begin, we have to take this 1,200 meters and convert it into kilometers. I could go meters per second here, but I don't want to. I'd rather do it this way. It works fine either way. Okay. So what I'm going to do is, as usual, we're going to use our unit conversion factor. So there's 1,200 meters times 1 kilometer over 1,000 meters. Okay. When I multiply that out, my meters cancels out and I get left with kilometers. So my distance is now going to be 1.200. It's important to keep the same number of significant digits, okay? Kilometers. All right. So what I'm going to do is go back to my knowns here, and I'm going to get rid of, or at least I'm going to try to get rid of, for some reason it's not cooperating with me. Why is this not working, guys? There we go. I want to get rid of this. Instead of writing 1,200 meters, I'm now going to write 1.200 kilometers. Okay, so basically now, these guys, I say they can talk to each other. They're now speaking the same language because they have the same unit in them. Now we can actually do this question that's being asked of us. But I am going to run out of space, so I'm just going to try and zoom out a little bit here. There we go. Okay. Hopefully you guys can still read that, but if not, that's okay. All right. So I am going to erase this unit conversion here, okay? But the next thing we're going to do is figure out our formula. So the formula that we always have is V is equal to D over T. That's how it's written in your booklet, which is why we always start here, all right? But now this time we're trying to solve for time. And this one's a little bit tricky because it's not super intuitive how to rearrange it, all right, so follow along with me here. It's going to be a little weird, but again, we want to undo everything that's being done to time. The problem that we have is right now we're technically dividing by time, and so what we want to do is get it out from underneath this line. All right, so the opposite, the way to get it out from underneath here is to actually multiply by time again. All right, so I'm going to get rid of my little arrow that I drew because I don't like it being there. Okay, so what we're going to do here is we're going to multiply by time again. And because we do that, we also have to multiply this side by time. Okay, over here, time cancels out, which is good. That means we got it out from underneath there. So one thing I hope you guys understand from this compared to the last one that we rearranged is the first step to rearranging this formula, anytime you have to rearrange it, is always multiply by t first. Okay, every time. And it seems weird to do that here, but it will make sense in a second. Now our formula, as it's currently written, is t times v equals d, which is exactly what we had on the last one. But again, I don't want distance by itself. I want time by itself. So we have to keep undoing everything we're currently doing to time. Time is currently being multiplied by velocity, so I want to divide by velocity. So I'm going to take this side of the line here, and I'm going to divide by velocity. I'm going to take this side and divide by velocity. Over here, velocity, or speed I should say, cancels out. And so I'm left with, when I do all this work, my new formula is going to be t is equal to d over v. Now I have velocity or time by itself, and I have to just divide my distance by my speed. Because I'm running out of room a little bit, I'm just going to erase some of this work that I've done. But if you're not sure how I did it, just take another, maybe go back another minute or so and just watch that rearrangement again. It's the only really tricky one. And the really weird thing is just the fact that you have to get this t out from underneath the line, out from being divided by. Okay? So if I delete that. Okay, and so now my formula that we just solved is t is equal to d over v. We have distance, we have speed, so all I'm going to do is plug those into my equation. All right, so all I'm going to do now is take those, plug them into the equation. So I've got my distance of 1.200 kilometers divided by 6.4 kilometers per hour. And so what happens here is because I'm dividing by kilometer, or multiplying by, or having kilometers on top and on the bottom, kilometers is going to cancel out, and all I get left with is hours. Okay, so when I put that in my calculator, what I get as an answer is 0.18. Can't read my own writing. 75 hours. Okay, now. Right now, I don't have the right number of significant digits, right? I should only have 2. But remember that the question says record or express your answer in minutes. So we have to take the 0.1875 hours and convert it into minutes. Okay, so I'm just going to zoom out a little bit more so I have a little more space to write. So what we're going to do here is our typical unit conversion. We're going to go 0.1875 hours times 60 minutes per 1 hour. That's our unit conversion factor. All right. And when I do that, what I get as an answer is basically 11 minutes after I do my rounding. Okay. So my final answer here should be 11 minutes as hours cancels out and I get left with minutes. So we did a lot of work there. It's only because the question made us do 2 unit conversions. Okay. Plus we had the hardest formula to rearrange. So if I go back to kind of where we were, so what we did there was first we had to convert meters into kilometers so that our units were talking in the same language. Okay, so we did that. From there, we had to rearrange our equation to get t equals d over v. All right. From there, we put our numbers in and divided, and then we had to convert to minutes at the very end to get our 11-minute answer. Okay. Those are the only 3 types of questions that I can ask you in this section. Okay, I can ask you for speed, distance, or time. That's it. So you just need to know those 3 formula rearrangements. If you're not sure how to rearrange the formulas, that's fine, but you will need to memorize the formula for distance and the formula for time. So just to summarize, our normal equation is for a uniform motion is v for speed is equal to distance divided by time. But I can rearrange that to find distance. Distance is equal to velocity times time, for the reasons that I showed you before. And time is equal to distance divided by velocity. All right? If you had a hard time understanding how I rearranged the formulas, that's okay, as I said, but it does mean you do need to memorize this guy and this guy, because this is the only one that's given to you in the booklet. Now, one thing that students like to use, and it's not something we recommend, but because we're trying to learn all this online, and it's not something I would normally teach you guys just because I'd rather you learn how to do it algebraically. But what I'm going to teach you guys is this little shortcut that you can use. Okay, I'm just going to scroll down a bit here. And a lot of students find this really, really helpful. Okay, so this is what we call a triangle type of formula. Okay, and what we do with our triangle is this. Okay, our D goes up here, V and T go here. Now it doesn't matter which way you put the V and T, what matters is that the distance is on top here. So the way you can use, if you're not sure how to rearrange, this triangle can actually help you out, all right? So let's say you were trying to find distance. What you do is you actually cover up this, maybe I can just block it with something here. Yeah, you actually cover this up, and you see how what I have down here is velocity and time side by side. That means we're going to multiply them together. So in other words, if I'm trying to find distance, you just cover up the one you're trying to find, and you get, it's velocity times time, which is the formula that I have here. If I wanted to find, why can't I get rid of my little circle? There we go. If I wanted to find velocity, time, I move this here, okay? You can see now that by trying to find time is equal to distance divided by velocity, which is the exact formula that we have here. If you wanted to find velocity, again, you just cover up this way. So velocity is equal to distance divided by time, which is the original formula that I give you. So if you're really struggling with the formula rearrangement, this triangle I find super helpful. And it does help students, especially if you're a bit weaker in math. This is a nice way to do things. What I'd like you guys to do for the rest of this class is to try and do the exam or the practice questions on page 3 of your book. There's 8 of them there. Do your best. Some of them are trickier than others, and the answer key is up on D2L. Hope you guys can make it to Tuesday's virtual class, and I will answer any questions you have. Hopefully you guys are doing great. I miss you guys. We will see each other again at some point. All right? Have a great day.